Welcome to FEMSA Medu Consultancy. Today we'll be looking at another aspect of mathematics called calculus, and precisely we'll be looking at reduction formula. Okay, now in the process of integrating trigonometric functions, there are tendencies for us to have trig functions to a particular integral power. Okay, for example, it's easier for us to integrate something like sine x dx. All right, it's easier for us to integrate cos x dx. Okay, because you can easily use the direct standard formula to be able to integrate this. You can easily integrate tan x and the likes. But when you now have the nth power of these trigonometric functions, like say for example cos cube x dx, okay, then we'll encounter some difficulties to use the standard integral formula to be able to integrate these functions. All right, so we will need something called reduction formula. The essence of reduction formula is to help reduce that power, in such a way that the resulting integration of the integrand is easy for us. All right, this is what I'm saying. Is there a way, for example, look at this cos cube x. Is there a way we can reduce this in such a way that the power can come to 2 or possibly 1? All right, so if there is a particular formula we can use to integrate this in such a way that the power will be reduced, and it makes it easy for us to integrate the resulting trig function, then that formula is what we refer to as the reduction formula. All right, so we'll be considering the reduction formula for the nth power of cos x, the nth power of sin x, the nth power of tan x, the nth power of sec x, the nth power of cosec x. All right, so but whatever principle we apply to any of these is similar approach we will need to make use for others. So but for today we are going to be looking at the reduction formula for the nth power of cos x. All right, so let's begin quickly. So one of the things we can do is that we can say let I want to dance around the first letter, okay, of this the n power of cos x. Let Cn, for example, now C sub n be equal to integral of cos x raised to power n dx. Okay, look at it. It's very important that you take note of what I am doing. This, I deliberately use C sub n to represent the integral of this. All right, you will see a reason why. You see the reason I did this as we progress. All right, because I know that something is going to come out that will make my representation easy. Look at it. So we have this. Now if I'm to produce, progress rather, I only said let Cn be equal to integral of cos x raised to power n, okay, integral of cos x raised to power n dx. So one of the things I need to take note of is recall from our laws of indices. All right, because this cos x raised to power n actually is the same thing as cos x all raised to power n. I hope you know that cos x raised to power n, this and this are the same thing. Okay, this is just the way we write it. Now then, if you remember from our law of indices, you will remember that x raised to power a multiplied by x raised to power b is same thing as what? x raised to power a plus b, and x raised to power a divide by okay, I can make use of this. Don't let me go to another one. This. So that shows that if I have x raised to power 2 multiplied by x raised to power 1, what would this give me? To give me x raised to power 2 plus 1, which is x raised to power 3. Alright? So that shows that I can rewrite this. I can rewrite x raised to power 3 as x raised to power 2 times x raised to power 1. This and this are the same. How did I arrive at this? It looks like I have said x raised to power 3 minus 1 multiplied by x raised to power 1. This and this are the same. As in, this is the same thing as this. This 2 is the same thing as 3 minus 1. I only manipulated this, okay, so that it will look like this. This, I manipulated x raised to power 2 to be in terms of x raised to power 3 here. So the same approach here, which means that what you are seeing here is the same thing as cos x raised to power n minus 1, 3 minus 1, times cos x. Do you see this now? That shows that this is like same thing as raised to power 1. If you add n minus 1 to 1, you will definitely get n. So I can split cos x raised to power n into cos x raised to power n minus 1 times cos x. I hope you are getting it. You see, I just have to go this way because the moment you master it for this particular one, that is the approach I will have to use for the other trigonometric functions. I don't have to do detailed explanation like this again. So if you want to understand all the approach I will need to make use of for integral of sine x raised to power n dx, integral of tan x raised to power n dx, integral of sec x raised to power n dx, the integral of cosec x raised to power n dx. Everything I will explain in that particular video, the details are here. So I may have to be fast in that. I may not need to go detail this way again. Are you getting it now? So try as much as possible to understand this particular aspect so that it's easier when you are trying to, evaluate those other functions yourself. Okay, so now look at this. So if this can be written, if this can be written this way, that means I can rewrite this as what? Cos to the n power of n minus 1 of x times cos x. Do you see it now? So I will go back and rewrite this expression just like this. Do you get it? All right. Don't forget, all of these principles are not, they are not difficult and they are not lengthy as it appears. But in the process of trying to explain, it makes the solution appears longer. But the moment you get the concept, you can try it yourself. You will see that within minutes, you are done with the reduction formula. Okay, so look at it. This becomes, I'll come here, c sub n equal to integral of cos n minus 1x times cos x dx. So I had split this into cos x raised to power n minus 1 times cos x. Okay, so what will now happen? What will happen now is that I'm trying to look for a way from here directly. Okay, I can apply my integration by parts. All right, but there are two ways to make it easy for yourself. Look at it. There are two ways of doing it. You can represent directly. When you look at it, which of these functions are easier to differentiate and which one is easier to integrate? Remember, we want to integrate cos x raised to power n dx, and it's difficult for us to integrate, so we have to break it down, splitting it into two products of two functions. okay, you will realize that it will still, if it's difficult for us to integrate cos x raised to power n, then it will still be difficult for us to integrate cos x raised to power n minus 1. So that shows that I would rather differentiate this and integrate this. Okay, remember our integration by part. From integration by part, all right, integral of u dv, okay, is the same thing as uv minus integral of v du. Do you get it now? So if you compare this integrand now with this particular integrand, I can simply say that my u can serve as, can be replaced with cos x raised to power n minus 1, while my dv will be replaced as cos x dx. Do you see it now? So this dv will be replaced with cos x dx. Do you get it? So it's as easy as that. Now that means that I may not need to transform anything here. I can just apply my integration by part directly. But some other approach, you will see something like this. This can be written like integral of cos x raised to power n minus 1. Then you see something like this, d sine x. And you'll be wondering, how did they approach it? Is the same approach, is the same thing. Okay, you need not to panic. What they did is still what we have done here. All right, they only replace cos x dx with d sine x. How and why? Look at it. Remember, if y is equal to sine x, y is equal to sine x, what is dy dx going to give you? Remember that dy dx will give you what? Cos x. Do you get it? If you decide to multiply both sides by this dx, what do you think you're likely to get? You will have, don't forget I'm still explaining, you have dy equal to cos x dx. If you decide to multiply both sides by dx, the one you call cross multiply, all right? So you will have this. Don't forget, what was our initial statement? If y equal to sine x, that means that anywhere I see y, I can replace it or I can represent with sine x. Do you get it? So look at it. Can you see my y here? I can remove this y and replace with sine x here. That means this will imply that what? D sine y, sine x. D sine x is equal to cos x dx. Do you see it now? That anywhere I see cos x dx, it can be replaced with what? D sine x. It is just a small substitution, okay, using the residual knowledge of your differential calculus. Do you understand now? How that came to be is just to think of what can you differentiate that will give you this sine x, this cos x. That particular that particular expression you will differentiate, or that particular trig function that you will differentiate that will give you cos x is what you put inside that is what you put beside this d, okay, as though you are differentiating sine x to be able to get that cos x. Do you get that now? All right, so either you decide to replace this in this form first, okay, or you go straight to do your representation. However you do it, you'll be correct. Do you understand now? So permit me, okay, to use this approach. All right, if you use this approach, you will get the same thing. See what you're likely to get here. on getting to using integration by parts, when you get to this side, you will differentiate both sides. Okay, you differentiate this with respect to x. When you differentiate this will give you du dx, and if you differentiate this, you will have n minus 1 cos n minus 2x, then you now have minus sine x. From here, I'll still do it, I'm just quickly writing that. Then here, on getting to this is dv equal to cos x dx. What you need to do here is to integrate both sides. Alright, the moment you integrate both sides, you will have integral of dv is equal to integral of cos x dx, and this one would mean that you are integrating dv. When you integrate dv, you will definitely get your v. It's like integrating a constant. Are you getting it? It's like integrating 1 dv, and if you are integrating 1 with respect to v, what will you get? You get v. Alright, so it looks as if the integral sign terminates the differential sign, so you have v. And when you integrate cos x, what are you likely to get? You get sine x. So this will become sine x, and that's all. And if you follow this particular one, where is it said? Here, our d sine x. If it is this one, that means your representation will just be dv is equal to d sine x. And if it is this, what will you now do? You integrate both sides, integrate this, integrate. So it will look like you are integrating 1 with respect to v, and what will you get? You get v. And it will also look like you are integrating 1 with respect to sine x. What will you get? You get sine x. So either of the two methods, you will get the same result. Now, the advantage of this one is that if you have done the proper substitution, whatever your result of integration is the one that is hidden inside this differential differential sign, okay, or this differentiation of this, and what is beside this differential sign, which is sine x. The result of your integration is what you will see here directly. Okay, unlike here that you have to do the integration. Whichever method you want to choose, you will be correct. Okay, so let's move ahead now. So now from here, I will have integral of cos x raised to power n minus 1. Then I'm replacing this with d sine x. Alright, so what do I do next? Look at me. I'm going to say that I want to use integration by parts now. Using integration by parts, I'll say let my what? My u equal to what? Equal to cos x to the power of n minus 1, and my dv, okay, will become this will become d sine x. All right, okay, so what would that give me? Can I get my du dx here? So my du dx, I'm differentiating this. What will you get? Remember that if you have y equal to x raised to power n, what do you have as your dy dx? Dy dx will be what? N times x raised to power n minus 1. You remember that? So now, suppose this x, look at it, you have if y is not x. Now this time around, if it's a function of x and it's now this way, all right, what the formula, you can use chain rule here. Our dy dx, in this case, it will follow this format too. N times function of x raised to power n minus 1. But because this is not x but a function of x, then we will need to differentiate it and multiply with our initial result. So that means differential of this, I'm tagging it as f prime of x. Do you get it? An example of this is when you have if you have y is equal to 2x plus 1 all raised to power 2. Okay, you will first, to get your derivative, you will have to also follow the format as if you are looking at x. So this will first be 2 multiplied by 2x plus 1 raised to power 1. You have removed 1, okay? Then you now multiply your result with the derivative of that function of x. This is now seen as a function of x. So if you differentiate this, what would that give you? This will give you 2 and this will give you 0. 2 plus 0 is 2. So you are multiplying by 2. Alright? That's the same thing that will happen here. So look at this. If y is equal to cos x to the power of n minus 1, and you want to find the derivative of this, the derivative will be what? This is like the power. Following it, you are going to have n minus 1 cos, what do you do? Remove 1 from the power. That will be n minus 2x. Would that be your final result? No. Because this cos x, you are seeing this thing as cos x raised to power n minus 1. This one now is now a function of x. What do? Differentiate it. What will you get? You get minus sine x. Then you multiply by minus sine x. Do you understand? So that's the same thing I'm going to apply here. So derivative of this is going to give me, I'm merging them together now, alright? So that will give me n minus 1 cos to the power of n minus 2x, then times minus sine x. So if you merge them together, look at me. I need to do something here to make it fast for us, okay? If I tell you my dy dx is equal to 3x, do you know that if I multiply both sides by dx, what will I get? I will have dy, all right? It will be equal to 3x dx. Do you understand that? So that means that I can multiply both sides by dx while trying to rearrange this. This negative sign multiplies this. So I'm going to have, it implies that I have du equal to minus n minus 1 cos to the power of n minus 2x. Then I now have sine x. I will keep that. Okay? I don't need to rub out this other part. Don't mind how lengthy the explanation is. It's just for you to be able to. Okay. Oh. I need to do something here. That is for our du. Here, what's our dv? And what do you do in this place? You integrate both sides. Integral of dv is equal to integral of d sine x. And what do you do here? When you integrate with respect to v, you integrate a constant with respect to v, you get your answer in terms of that v. So the result of this integral is what? V, and the result of this integral is what? Sine x. Alright, like I said, it looks as if the integral nullifies this differential sign. the integral nullify this differential sign, so that the result you get is v, you get sine x. Okay, but it looks like you are integrating a constant. The constant here is 1. The constant here is 1, and when you are integrating that constant with respect to v, you get v. Just like you are integrating 1 with respect to x, what do you get? You get x. So if I'm integrating 1 with respect to sine x, you get sine x. Do you understand? So we keep this in our mind. Okay, then we'll now come back to this representation. So it is this we will take back to this. Alright? Because we are simply saying we should let our u be equal to this, and we should let our v to be this. Okay, so what that will imply, it will now imply that our c sub n will now become, don't forget we have let. Okay, what are we going to have? Anywhere we see cos x to the n to the power of n minus 1, what do we have? We have u. Then you have, anywhere you see the sine x, we can replace with the v. That's it. I have replaced it. Okay, now that I have done that, our duty now is what will be the result of this particular expression. So from our knowledge of integration by parts, this can be written as uv minus integral of v du. And what would that give us? I will now come back. What is my u? My u is cos x to the power of what? N minus 1. So this will give me, don't forget all this represents c sub n. So I will have cos x raised to power n minus 1 x. Then my v is what? Sine x. Do you get that now? So this is going to be equal to sine x. So that settles that. Okay, so the next one is this. My v again. So the u is this and v is sine x. So the next one, minus integral of don't mind my board though. So my v is sine x. And my du is all these expressions here. This will be a bit long. Okay, let me see what to do to. All right, okay, let me put it down so that you will see. Let me see. Then go minus here, minus integral of, I want to put it down here, integral of sine x. Then my du is times minus into n minus 1 cos x raised to power n minus 2x, then sine x. Oh, there should be dx here, sorry. Remember I said we should multiply both sides by dx, so there should be dx there. So this should now have dx, because you must integrate with respect to a particular variable. So we are integrating with respect to x. Don't forget there is a minus sign here. Okay, or better still, maybe I should put it here, so that we have this minus this. So now this will become c sub n equal to cos x raised to power n minus 1 x, then sine x. Then I have minus, if I multiply this, sine x times sine x will give me what? Sine square x. Then this is a constant, n minus 1 is a constant factor, okay? So and it has negative. So if this negative and n minus 1 are being factored out or being brought out of this integration, this sign will multiply this sign, it becomes positive. Then I have n minus 1 outside, okay? Because I am integrating with respect to x, and this expression here is independent of x, it does not contain x. So it's seen as a constant, you can bring it out of the integral sign. You get it? So this will now become integral of, this will now become sine square x, then this will become cos x raised to power n minus 2x dx. Wow, we are progressing, right? Okay, so what's the next thing to do? Look at it. I'm going to have cos x raised to power n minus 1x times sine x. Okay, plus I will have n plus minus 1 rather integral of, then I will have to remember again, okay, that sine x, sine square x can be written in terms of cos x, precisely cos square x now, using our identity formula. Remember that what? Sine square x plus cos square x, what will it give me? It will always be 1. So if I make sine square x the subject of the formula, what will I have? It means sine square x will be what? 1. Transfer this here, you have minus cos square x. So anywhere I see sine square x, I can replace with 1 minus cos square x. So that's what will happen here. So this will become 1 minus cos square x in brackets. Then I have cos x raised to power n minus 2x dx. We are progressing. Now, don't worry, it's not difficult, okay? If you take it step by step, you will definitely get it. In fact, after watching this video, okay, put it aside and practice it yourself and see if you can follow the same pattern and get the same result. Try it over and over until it stays in your cerebrum. It's very important. And once you have known it, the next thing you have to do is just master the expression for the reduction formula for cos x to the nth power. Do you understand now? I think for your own level, precisely your own JUPEB exam now, what you will need it for, you will only need the expression. You see that the derivation is a bit lengthy, okay? And I'm not too sure they want to test you on that. They only want the application. But even if you are to now remember the expression, if you have forgotten, what will you do? You have to quickly use this approach. Do you understand now? But the moment you engage the expression often, you realize that there's a way it will stay. By the time we finish now, you need to learn the pattern of that expression. All right? So permit me to rub out this aspect now because I need to progress with this side. So what do we get from here? It means that our c sub n will become cos x to the n minus 1 power of x. Okay, cos x to the n minus 1 power, then multiply by sine x. Then this should give us what? Plus, okay, let me do it this way so that it is easier. This will give me, if you open the bracket, what do you have? Cos x to the n minus 2 power times 1 will give us this cos x raised to power n minus 2 minus, by the time this and this multiply, it's like multiplying x squared times x minus like this. What will this give us? This will give us x raised to power 2 plus n minus 2. So 2 minus 2 is what? 0. And this will give us what? X raised to power n. Which means that when you multiply this and this, it's like this 2 terminate this minus 2. So that our result will give us what? Cos x to the nth power. Then everything with respect to x. Okay? Don't mind me, I'm trying to squeeze my board. But follow my sound, my voice rather, with what you are saying. You should be able to see, get it. Let me write it here so that you can see it. C sub n will become cos x raised to power n minus 1 sine x plus. So now what I'm going to do is that this integral sign is a linear operator, and if I apply linearly on this integrand, okay, it will give me n minus 1 integral of cos x raised to power n minus 2x dx minus n minus 1 integral of cos x raised to power n dx. This was what I meant by integral sign being a linear operator. If you have integral of a plus b dx, I can write it as what? Integral of a with respect to x plus integral of b with respect to x. Okay, it's a linear operator. I can integrate these terms, okay, individually. All right, so that's what I applied here. But this constant outside will multiply whatever results I obtain from this integration. So I will have this. Please don't mind my board though. Okay. All right. So the result of this will be what? This will give us cos n minus 1x sine x. Now, remember I said we represented that what? Remember this, if c sub n is the same thing as cos x raised to power n dx. I said something earlier when we did this representation. Look at it. What do you notice? C sub n integral of cos x raised to power n. What do you think c sub 2 will be if you follow this pattern? Okay, you will realize that will give us integral of what? Cos square x dx. Do you understand? I'm just playing with this n. Okay, where n is a positive number or positive integer. All right, so what is going to be c5 going to be? That's going to be integral of what? Cos x raised to power 5 dx. Don't forget, I'm just playing with that number. So the same way, what do you think c sub n minus 2 will be? That will be what? Cos x raised to power n minus 2x dx. Cos x raised to power n minus 2 dx. Do you see it? What do you observe here? Cos x to the power of what? N minus 2. That shows that I can rewrite this nonsense plus n minus 1. I can rewrite this as c sub n minus 2. What that means is that it's just a representation that anywhere I see c sub n minus 2, what it means is integral of cos x raised to power n minus 2. That's what it means, what it means rather. Okay, so this will become n minus 1. Then this one is what? C sub n. It's a representation. So what will I do? Don't forget that this is c sub n. I will not try to look for like terms. You see that this and these are like terms. Why are they like terms? Because it's in terms of c sub n. Okay, this one is in terms of c sub n minus 2. So bring this to this other side, which means you are adding n minus 1 c sub n to both sides. And once you do that, you are going to have n minus 1 c sub n plus c sub n. It will be equal to what? Cos x raised to power n minus 1x sine x plus n minus 1 c sub n minus 2. Don't worry, like I said, that I don't expect them to ask you to prove this, but for those in 200 level, okay, who will be taking mathematical methods, they cannot escape proving this reduction formula. All right, or they can't escape regular application of this reduction formula. Okay, so for now, do not panic. You just need to know the procedure, but it's not out of place if you take your time to go through the process step by step. okay, and practice it. Practice it until it becomes part of you. Do you understand? So now this will now become n c sub n minus c sub n upon multiplication. This will be n c sub n, this will be c sub n, then plus c sub n equal to cos n minus 1 x sin x plus n minus 1 c sub n minus 2. So this will terminate this because minus this plus this is going to be 0. So what do we have? I'll have n c sub n left equal to what? Cos x raised to power n minus 1x sin x plus n minus 1 c sub n minus 2. Alright, so what do? We will now have, I'm looking for this, don't forget that we want to look for integral of cos x raised to power n dx, which we have represented with what? C sub n. And this is my c sub n here. Okay, so I'm to make it the subject formula, and to do that I will have to divide both sides by n. Okay, so this will give me c sub n will become, I'm dividing both sides by n. So it looks like I am dividing through, because if this n will come here, look at it. So I need you to get this. If you have a plus b divide by c, do you know that this is the same thing as what? A over c plus what? B over c. Do you understand now? That's the same way. Because of this addition here, by the time I divide both sides by n, there will be division of n here. Okay, once you have divided by n, I can use it. I can also decide to write it as 1 over n cos n minus 1x sin x, okay, plus n minus 1 over n minus 2. So I can put this in a bracket. So you see the beautiful result is out already. Let me show you what this means. Is therefore our integral of cos this with respect to x is equal to 1 over n cos x raised to power n minus 1 sin x plus n minus 1 over n cos c sub n minus 2. What does this mean? I'll put it like this, n minus 2. I'll now say where c sub n minus 2 is integral of what? Cos x raised to power n minus 2 dx. So this is the expression we are looking for this. Okay, or let me put it directly so that you will see it clearly. Integral of cos x raised to power n minus 2 x dx. So, but this is the reduction formula we are talking about. Now, do you notice that the power of cos x is reducing gradually? Alright? It's reducing gradually. But it will get to a point, it will terminate. Now, look at it. If n is an even number or even integer, okay, precisely now, you will see that this thing will continue. I'm going to take an example now. You see that it will continue, and your last term, okay, the last expression will be in terms of 1. Because, for example, if n is 2, what do we have? 2 minus 2, that will be 0. Then you're going to have cos x raised to power 0, and cos x raised to power 0 is what? Is 1. So that means you're going to have integral of 1 dx, which is the same thing as integral of dx. And what would that give you? X. It's like integrating a constant with respect to x. Do you understand now? And if your n, which means that this reduction formula, if let me quickly put it this way so that you will see it. What that means is that if n is even number, comma, then this will terminate to 0. All right. So that therefore integral of cos x, this with respect to x will approach x. That means that if n is even, this will keep reducing until the last term, by the time you integrate it, it must be x. But if it is odd, you will see that the integral of this, the smallest part will become 3. Okay, and that will give us integral of cos x. And when you integrate this, you must definitely end with sin x. Don't worry, when I take an example now, you will see what we are saying. All right. I want to see if I could illustrate this on a general note. There's a way I can do this reduction, but I think for now you have seen the reduction formula. So what you need to master is this, that the integral of cos x raised to power n is the same thing as 1 over n cos x raised to power n minus 1 sin x plus n minus 1 over n, then c sub n. That means integral of cos x raised to power n minus 2. Do you understand? I think the best thing to do is still just to use an expression. It will always follow this pattern. If I give you, for example, now, okay, let me do that in another, but that's the reduction formula. So we are going to see the application of the reduction formula in the next video. I hope you have learned something. I pray that which you have learned in this particular expression or this particular video is retained in your cerebrum in the name of Jesus. I declare that you won't make mistake in the course of writing your exam. You will apply these principles appropriately in the name of